What if the ground under one of the most watched fault lines in America just sent a warning and almost nobody noticed? Well, every camera on Earth was pointed at Japan this week. A quiet fault in California moved for the second time in 5 weeks, and scientists are not calling it a coincidence. Before we go any further, if you want to actually understand what is happening under Northern California right now, hit like on this video, subscribe if you are new here, and share this with one person who still thinks earthquakes only happen without warning. It genuinely helps this channel keep making videos like this one. Now let's get into it. On Tuesday evening at 7:40 p.m., the ground moved near a small town called Cloverdale in Northern California. It was not a huge earthquake. The United States Geological Survey measured it at magnitude 4.3. That is the kind of earthquake that normally makes a small headline and disappears by the next morning. Nobody was hurt. No building fell down. People felt dishes rattle and pictures shake on the wall, and that was about it. But here is the part that should have made this a much bigger story. Within hours, scientists recorded more than 160 smaller earthquakes connected to this same event. Not one or two aftershocks, over 160. And the USGS did something it does not do casually. It labeled this 4.3 earthquake as a possible main shock, meaning the earthquake itself might not be the biggest thing coming from the sequence. It might just be the beginning. Let that sink in for a second. A magnitude 4.3 earthquake should produce maybe a dozen small aftershocks at most. And then everything should go quiet within a day or two. Instead, this one lit up more than 160 separate events. That is not normal behavior for a small earthquake. That is the behavior of a much larger section of underground rock that is already under stress and ready to move. Scientists actually have a rough mathematical rule for how aftershocks are supposed to behave. It is called Omori's law. And it basically says that aftershocks should come fast right after the main event and then fade away quickly, following a predictable curve. Most small earthquakes follow that curve almost perfectly. A handful of aftershocks in the first hour, fewer the next hour, and by the next day, things go mostly silent. When a sequence blows past 160 events and keeps producing new ones well beyond what the curve predicts, scientists pay attention, because it usually means the earthquake did not simply relieve stress in one small spot. It disturbed a much wider area that was already close to its breaking point. Think about it like a stack of dishes leaning against each other on a shaky table. If you tap just one dish and nothing else moves, that is a small, contained event. But if you tap one dish and suddenly the whole stack starts wobbling and shifting, that tells you something different. It tells you the whole stack was already close to falling before you even touched it. One small tap should never be able to shake an entire stack like that unless everything in it was already balanced right on the edge. That is exactly what scientists are seeing here. This earthquake did not act like an isolated event. It acted like something woke up a much bigger, much more stressed piece of the Earth's crust. Now here is where this story gets even more important. The earthquake near Cloverdale happened directly on a fault most people outside of science have never even heard of. It is called the Maacama Fault. It runs through the hills of the Northern California coast, not far from the more famous San Andreas Fault that everyone already knows about. And even though almost nobody talks about the Maacama, it carries a serious amount of the slow, grinding motion between two massive tectonic plates that are constantly pushing against each other underneath the west coast. Here is something fascinating about this fault. Scientists have measured that it moves at a slow, steady rate every year, a few millimeters at a time. Some of that movement happens quietly through something called creep, where the two sides of the fault slide past each other gradually instead of snapping suddenly. You can actually see the evidence of this creep in real life. Curbs, sidewalks, and fences that cross the fault line have slowly shifted sideways over the years, just from this constant, gentle sliding. For a long time, that creeping motion has been treated almost like a safety valve. Something that quietly releases pressure so a big earthquake never has to happen. But scientists who study this fault closely say that idea is only partly true. Yes, creep releases some of the stress, but it does not release all of it. A portion of that pressure keeps building underground, year after year, stored as tension in the rock. It does not disappear. It waits. Imagine slowly bending a thick tree branch, just a tiny bit every single day. Some of that bending relaxes on its own overnight, but not all of it. A little bit of tension stays locked in the wood every single time. Do that for years, and one day, that branch is not going to bend anymore. It is going to snap all at once, releasing everything it had been quietly storing the entire time. That is essentially what is happening underground along this fault, just on a time scale of decades instead of days. And that brings us to something that happened just 5 weeks before this week's earthquake, something that makes this entire story far more serious. On the morning of June 24th, a much bigger earthquake struck the same general area, close to a small town called Ukiah. This one measured magnitude 5.6, and its center was almost directly beneath a quiet mountain monastery. It was the strongest earthquake recorded in that region in almost 90 years. And more importantly, it was the strongest earthquake ever officially linked to the same Maacama Fault in the entire history of modern earthquake recording. The shaking near the center was intense. Thousands of people felt strong to severe shaking. Thousands lost power. There was minor damage, and some people were injured. California's earthquake early warning system, called Shake Alert, activated and sent alerts out to nearby residents. But here's an uncomfortable truth that came out of that event. If you're standing almost directly above where an earthquake starts, an early warning system cannot save you much time. The warning signal travels at the speed of light. The actual shaking travels much slower through rock. So people far away can get a real head start, sometimes 20 or 30 seconds, which is genuinely enough time to take cover. But people sitting right on top of the fault get little to no warning at all, because the earthquake has to start before anything can detect it. That is not a flaw in the technology. That is simply how physics works. Warning systems can detect earthquakes. They cannot predict them before they happen. So now line these two events up. A magnitude 5.6 earthquake on June 24th, the strongest ever recorded on this fault. Then, just 5 weeks later, a magnitude 4.3 earthquake with an enormous swarm of over 160 aftershocks, happening about 35 miles away on the same general fault trend. Two significant earthquakes, 5 weeks apart, on a fault that had never before produced anything above magnitude 5.6 in its entire recorded history. Does that guarantee something bigger is coming? No. Earthquake history in California, in terms of modern recorded data, is actually pretty short. Compared to the deep timescales the Earth works on, sometimes a short record can make a pattern look more dramatic than it really is. But what this does prove, without question, is that a fault almost nobody was paying attention to has now clearly shown, twice in about a month, that it is actively active. It is not sleeping. It is moving. If this kind of thing genuinely interests you, now is the perfect time to subscribe. Because we are going to keep tracking this fault as new data comes in, and you do not want to miss the moment the pattern actually shifts. Now let's dig into why this fault's deeper history matters even more than what shows up on modern instruments. Scientists have gone back and studied ancient soil layers near a town called Willits, right along this same fault. By carefully digging through the layers of earth, they found clear signs of several large earthquakes on this fault going back hundreds of years, long before anyone had instruments to measure them. Researchers were careful not to assign exact numbers to these ancient earthquakes, because turning old soil layers into a precise magnitude is not really solid science. But based on how much the ground had shifted in those old layers, many researchers believe those earlier earthquakes were likely somewhere around magnitude 6.5 to 7, or possibly even bigger. To understand how huge that is, you need to understand how the earthquake scale actually works. It is not a simple straight line. Every single step up in magnitude represents roughly 30 times more energy released. So an earthquake at magnitude 6.5 does not release a little more energy than one at magnitude 5.6. It releases roughly 30 times more. A fault that keeps quietly creeping and still manages to produce earthquakes that large in its deep history is a fault where creep clearly is not enough to release everything safely. Some of that pressure is still being saved up for a much bigger release, sometime, somewhere down the line. Now follow this same fault trend further south. And this stops being just an interesting science story. It becomes something that touches millions of people's daily lives. If you trace the general direction this fault system runs, it eventually connects to another fault called the Rogers Creek Fault, which continues down through wine country toward the edge of the San Francisco Bay Area. For years, scientists were not completely sure what happened to this fault once it reached the bay itself. Did it just stop? Did it connect to something else? In 2016, researchers using detailed underground imaging finally solved that mystery. They discovered that the Rogers Creek Fault and the Hayward Fault are actually physically connected underneath the bay. The Hayward Fault runs directly underneath some of the most densely populated cities in the East Bay. Together, they form one long, continuous fault system, stretching roughly 118 miles. Here is the number that should make anyone living in the Bay Area sit up and pay attention. If this entire connected fault system were to rupture all at once, from end to end, scientists estimate it could produce an earthquake of roughly magnitude 7.4. To put that in perspective, that would release something like 700 times more energy than June's magnitude 5.6 earthquake near Ukiah. Before we go further into this, quick pause. If your mind is already racing through what this means for the Bay Area, that is exactly the reaction this video is meant to create. Drop a comment telling me which fault worries you the most where you live. Hit that like button so this reaches more people who need to see it. And if you have not subscribed yet, now is a good moment to fix that. Now, before anyone panics, let's be completely honest about what this does and does not mean. A magnitude 4.3 earthquake near Cloverdale does not directly add stress to the Hayward Fault. They are too far apart for that kind of direct physical connection. Scientists are very clear that this small earthquake is not somehow loading up pressure on a fault dozens of miles away. That is not how it works, and nobody credible is claiming otherwise. What actually matters here is not a direct cause and effect. It is something bigger picture. This recent earthquake activity is happening at the northern tip of one long connected fault system that eventually runs straight through the most crowded, most built-up part of Northern California. And the deep history of that northern section shows earthquakes far larger than anything that has shown up in modern records so far. That gap between what the fault has done in the deep past and what it has done in recent history is exactly the kind of gap that keeps earthquake scientists up at night. There's also something else worth clearing up, because it can easily get confused with what we are talking about. Not far from Cloverdale, there is another cluster of small earthquakes happening near a place called the Geysers, which is home to the largest geothermal power field in the entire world. That area produces small earthquakes too, but for a completely different reason. Pulling steam and water out of the ground for energy causes the rock underground to shrink slightly, and that shrinking creates small, shallow earthquakes. This is well understood, well documented, and openly discussed by both scientists and the companies running that facility. It stays contained to a small area and is a completely separate process from what is happening on the Maacama Fault itself, which sits many miles away. Two different processes, showing up close together on the same map, but not related to each other at all. Now let's talk about why this story barely made headlines in the first place, because the timing here matters a lot. About 27 hours before the ground moved near Cloverdale, a much more serious earthquake struck Japan. It hit the island of Kyushu in an area called Kumamoto, and it measured somewhere between magnitude 6.8 and 7.1, depending on which agency you check. This was a shallow earthquake, and it hit hard. It registered the highest possible reading on Japan's shaking intensity scale, a level that has only been recorded a handful of times in the country's entire history. The damage was serious. At least one person died. Dozens of people were injured. Part of a shopping mall collapsed, and shortly after, an explosion tore through the building, blowing out walls and exposing its steel frame. That same mall had only reopened about 6 weeks earlier, after being rebuilt from an even bigger earthquake back in 2016. Roads cracked apart. Fires broke out. Hundreds of thousands of people had to evacuate. Naturally, with a disaster this serious unfolding in real time, the entire world's attention turned to Japan. And a quiet fault system in California, one that most people had never heard of, barely made the news at all. Japan is one of the most earthquake-ready countries on the planet. Its buildings are engineered to sway instead of crack. Its warning systems reach phones in seconds. Its people practice evacuation drills the way other countries practice fire drills. And yet, even with all of that preparation, this earthquake still managed to injure dozens of people, destroy part of a shopping mall, and force hundreds of thousands of people out of their homes. That should tell you something important. No amount of preparation makes an earthquake harmless. It only makes the difference between a tragedy and a catastrophe. Readiness saves lives, but it does not stop the ground from moving. But here is the part that connects these two stories in a way that should genuinely give you chills. Back in April 2016, almost this exact same region of Japan experienced something eerily similar to what just happened in California. A magnitude 6.5 earthquake struck the same general area. At the time, everyone treated it as the main event. Emergency crews responded, and people who had evacuated their homes started moving back in, believing the danger had passed. Then, about 28 hours later, a magnitude 7.3 earthquake struck the exact same fault system. That first earthquake, the one everyone thought was the big one, was only reclassified afterward, once the second and far more devastating earthquake hit. In hindsight, it was not the main event at all. It was just a warning tremor. This is exactly why scientists are being so careful with their wording when they describe what happened near Cloverdale this week, calling a magnitude 4.3 earthquake. A possible main shock is not just careful language. It is an honest admission of a real limitation in earthquake science. There's currently no way, none at all, to look at an earthquake the moment it happens, and know for certain whether it is the big one or just an early warning tremor before something larger. That difference can only ever be known afterward, once it is too late to change anything. Now, let's be fair to the actual statistics here, because panic is not the goal. Understanding is, based on decades of earthquake data, after any given earthquake, something larger follows within about a week, roughly 5% of the time. That means about 19 times out of 20, nothing bigger happens at all. And the earthquake you just felt really was the main event. So statistically, this week's magnitude 4.3 earthquake near Cloverdale is very likely to end up being the largest earthquake of its own sequence. But here is the uncomfortable truth hiding inside that reassuring number. That small percentage where something bigger does follow cannot be identified in advance by any scientist, any instrument, or any warning system currently in existence. In 2016 in Japan, that exact scenario played out, and it was only recognized 28 hours too late. This is not a hypothetical risk. It has already happened on a strikingly similar fault system in strikingly similar circumstances. Japan's own Weather and Disaster Agency is applying that hard lesson right now, warning residents in the hardest hit areas to prepare for the possibility of another strong earthquake in the days following this week's disaster. That warning is not based on some secret prediction. It is standard procedure, built directly from what was learned the painful way back in 2016. This is not the first time California has lived through the shock of a small warning tremor being brushed aside, before something much bigger followed. In 1989, the Loma Prieta earthquake struck the San Francisco Bay Area during a World Series baseball game, collapsing a section of a major freeway and killing dozens of people. And even further back, the 1906 San Francisco earthquake, one of the most destructive earthquakes in American history, ruptured a massive stretch of the San Andreas Fault and left the city in ruins and fire for days. Neither of those disasters arrived with a clean, obvious warning sign that anyone at the time could point to with confidence. That is the uncomfortable pattern running through almost all of earthquake history. The signs are usually there somewhere in the data. What is missing is certainty about which signs actually matter until after the fact. So, what should you actually be watching for if you want to understand where this is heading, whether you're in California or anywhere else in the world with active fault lines nearby? The answer is not really about waiting for one big scary number. It is about watching the pattern the aftershocks make. If small earthquakes following a big one stay clustered tightly around the same spot, that is generally a good sign. It usually means the stress is settling down normally, releasing safely, and calming toward quiet. But if those aftershocks start spreading out, stretching further along the direction the fault runs, that is a very different and more concerning signal. It suggests the stress is not just fading away. It is moving, spreading onto nearby sections of the fault that were not directly involved in the first earthquake. And that spreading pattern is exactly the mechanism that can sometimes turn a moderate earthquake sequence into something much bigger. For the Cloverdale sequence specifically, scientists have laid out a clear number to watch. There is roughly a 1 in 4 chance of at least one more earthquake of magnitude 3 or higher within the following week of this week's earthquake. If that happens, and it stays clustered close to where the current activity already is, that is a reasonably reassuring sign. But if it starts appearing further along the fault line, spreading toward new ground, that would be the real signal worth paying attention to, long before any single dramatic headline ever could. This is why scientists who study earthquakes rarely get excited about a single number. A magnitude by itself only tells you how strong one moment was. It does not tell you what the ground is planning to do next. The real story is always hidden in the pattern, in how the aftershocks line up on a map, in how quickly they fade or how stubbornly they keep going, and whether they stay boxed into one small area or start creeping outward like a crack spreading across a windshield. That is the difference between reading a headline and actually understanding what is happening beneath your feet. There is also a very human side to all of this that numbers alone cannot fully capture. Somewhere in Sonoma County right now, there are families who felt their dishes rattle on Tuesday night and went right back to their evening because nothing collapsed and nobody got hurt. There are people in Kumamoto tonight who cannot go home at all, sleeping in evacuation centers, waiting to hear whether their neighborhood is even safe to return to. Two very different outcomes from two earthquakes on two sides of the same ocean, separated by less than 30 hours. That gap is not random luck. It comes down to depth, distance from population centers, building codes, and simple timing. The same amount of shaking in a different location, at a different depth, hitting a more crowded area, can be the difference between a story nobody remembers and a disaster nobody forgets. Before we get to how this all wraps up, one more thing. If a video like this actually helps you understand the news instead of just fearing it, that is exactly what this channel is built for. Give it a like so more people see it instead of the fear-driven headlines everyone else is posting. And subscribe so you are already here the next time the ground has something to say. Here is what makes this story so important, and honestly, a little humbling. We live on top of a planet that is constantly shifting beneath our feet, mostly in ways too small and too slow for us to ever notice in daily life. Most of the time, that shifting happens quietly, safely, without hurting anyone. But every so often, the Earth sends a signal, a small tremor, a swarm of aftershocks, a fault nobody was watching suddenly waking up twice in the same month. These signals are easy to miss when the world's attention is somewhere else, focused on a much louder disaster happening on the other side of the ocean. But the Earth does not care what the news is covering. It moves on its own timeline, following its own rules, whether we are watching or not. It is worth remembering that the entire west coast of the United States sits on the edge of the same restless boundary between two massive tectonic plates that shaped Japan's earthquake this week. Different fault, different ocean, same underlying force. The Pacific Plate and the North American Plate have been grinding against each other for millions of years. Long before there were cities or highways or people checking their phones for breaking news, Every fault we have talked about tonight, the Maacama, the Rogers Creek, the Hayward, even the San Andreas itself, is just one more place along that same enormous boundary, where the pressure has to go somewhere eventually. Some of it leaks out quietly through creep. Some of it gets released in small earthquakes nobody notices. And every so often, in a handful of places, a huge amount of it lets go all at once. What happened this week in California was not proof that a massive earthquake is coming. Nobody can honestly promise you that. Anyone who claims they can is not being straight with you. But it was proof of something else, something quieter and arguably more important. It was proof that the ground beneath one of the most populated regions in the United States is not finished moving. It is proof that faults we rarely think about are just as alive, just as capable, and sometimes just as dangerous as the famous ones that make headlines every year. Somewhere underneath those quiet hills in Northern California, pressure that has been building for decades, maybe even centuries, is still sitting there, patiently waiting for its moment. Nobody knows exactly when that moment will come. Nobody can know that yet. But now you know what to actually watch for. And you know why a small earthquake that barely made the news might end up mattering far more than the headlines this week ever suggested. This is also a reminder of something bigger than any single fault line. We tend to give our full attention to whatever disaster is loudest in the moment, and that is a completely human thing to do. Nobody can watch every corner of the world at once, but the quiet stories, the ones happening while our attention is somewhere else, are often the ones worth understanding the most, because they are still unfolding. Japan's earthquake this week is tragic, and it deserves every bit of the attention it is getting. But the quiet swarm of tremors under Northern California deserves a place in that conversation too. Not because it is guaranteed to become something dramatic, but because ignoring it will not make the pressure underground disappear. Understanding it, even just a little, is the only real tool any of us actually have, and that understanding is exactly what we are going to keep building together. Video after video, as this story keeps unfolding. If you made it this far, you already understand this story better than most people who saw it flash by on their phone for 5 seconds and scrolled past it. That alone puts you ahead. Most people will only hear about this fault if it eventually produces the kind of earthquake that cannot be ignored. You now understand it while it is still just a quiet warning, while there is still time to actually pay attention instead of just reacting. So do one more thing before you go. Subscribe, turn on notifications, and stay with us, because the next update on this fault could come at any moment. And when it does, you will already understand exactly what it means, while everyone else is just starting to catch up.